All right, let's talk about complex calculus. I know, the name itself can sound a little intimidating. But what if I told you there's a secret weapon, a kind of master key, that makes some of its scariest-looking problems surprisingly simple?
So take a look at this thing. How on earth do you even start to solve it? We've got this integral, right? But it's not just moving along the x-axis. No, it's taking this crazy winding path through the complex plane. I mean, just looking at it, you'd think this is going to be a nightmare. And honestly, if you try to solve it the straightforward way, you'd be absolutely right.
Okay, so before we get to the cool trick, let's appreciate why we even need one. Let's take a quick walk down the long road, solving this thing by brute force.
So the traditional method is called parameterization. Basically, you have to describe that wiggly path with a variable t. Then you differentiate it, substitute everything back in, and then you're left with this beast of a polynomial to expand and integrate. I mean, look at all those steps. It totally works, don't get me wrong, but it is just so much tedious algebra. It's the kind of problem where one tiny slip-up with the plus or minus sign and the whole thing is ruined.
But what if there was a better way? A much, much better way. And the cool thing is, it's based on an idea that you've probably seen before way back in basic calculus.
And that idea is the antiderivative. You know this one, right? It's just the reverse of a derivative. It's the function whose derivative is the function you started with. Simple as that. And this is the whole foundation for our first secret weapon.
And that leads us to this, the Fundamental Theorem of Complex Integrals. And this is a total game changer. It basically says that if your function has a nice antiderivative, then the value of that integral doesn't care one bit about the crazy path it took. Winding, straight, doing loop-de-loops, it doesn't matter. All that matters is where you start and where you end.
All right, you ready for this? Let's go back to that scary-looking problem from the beginning, but now we're bringing our new secret weapon with us. Let's put this calculus on easy mode.
I mean, just look at the difference. On the left, you've got that whole mess of parameterization we talked about. And on the right, it's just 2 steps. That's it. Step 1, find the antiderivative of 4z cubed. Easy, that's z to the 4th. Step 2, plug in the endpoint and the start point and subtract. Boom, done. The answer is -5. Same exact answer, but we did it in, what, 10 seconds? It's just so much better.
Okay, that was pretty cool, but that was just the warm-up. That was secret weapon number 1. Now let's get to the ultimate power. What happens when the path gets even weirder? What if it's a closed loop, starting and ending at the exact same spot?
So you might be thinking, well, based on what we just learned, if the start and end points are the same, the answer should just be 0, right? And a lot of the time, you'd be right. But what if there's a problem inside the loop? A single tiny little trouble spot where our function goes haywire. That's when things get really interesting.
So to get to this next level, we need to talk about a special kind of function. They're called analytic functions. And honestly, you can just think of them as the superheroes of the complex plane. They're perfectly smooth, no weird jumps or sharp corners, and you can just keep taking their derivative forever without any issues. All the functions you know and love, polynomials, e to the z, they're all analytic.
And that brings us to this. This is the big one, Cauchy's integral formula. And honestly, this thing feels like actual magic. It says that if you're integrating around a closed loop and your function has this specific form, some nice analytic function on top divided by z minus some trouble spot, then the answer to that whole complicated integral is just 2 pi I times the value of the good function at that one single bad spot. Think about that. The value of an infinitely complex loop depends entirely on what's happening at one tiny point inside. It's unbelievable.
Okay, that might sound a little abstract, so let's put this formula into action. Let's tackle a problem that would be an absolute monster to do the long way.
All right, here's our problem. We've got this messy-looking fraction, and we need to integrate it around the unit circle. Trying to parameterize that thing? Yeah, let's just agree not to even think about it. Instead, we're going to use Cauchy's formula like it's a simple 3-step recipe.
And just watch how easy this is. Step 1, we just need to tweak it a bit so the bottom looks like z minus something. A little bit of algebra, and we see our trouble spot, z naught is I over 2. Step 2, we identify our nice superhero function, f of z. That's just the stuff on top. Step 3, apply the formula. We take 2 pi I and multiply it by our function evaluated at that trouble spot. And that's it. We're done. No integration, no parameterization, nothing. Just plugging in a number. It is so efficient.
So, okay,
This is obviously a great way to solve tough problems. But this isn't just about finding clever shortcuts for your homework. These formulas are telling us something really deep, something profound about how these functions work.
What Cauchy's formula is really whispering to us is a fundamental truth about analytic functions. It's telling us that if you know the value of the function all along the boundary, the edge of a loop, you automatically know its value at every single point inside that loop. It's like if you have a wire frame dipped in soap. The shape of the frame completely determines the shape of the entire soap film. There's no wiggle room. These functions are incredibly rigid, almost predictive in nature.
So let's just boil this all down. What are the big takeaways here? First, that winding path you see, it doesn't always matter. Thanks to the fundamental theorem, sometimes it's just about the start and the finish. Second, Cauchy's formula is like a magic trick that links an entire loop integral to the behavior at one single point. And what does all this mean? It means these special analytic functions are unbelievably structured. They're not random at all. They're incredibly predictable.
And that leaves us with a pretty cool thought, doesn't it? If a single point can hold the secret to an entire, complex journey in mathematics, what other simple keys are out there just waiting to unlock the complex worlds all around us? It really makes you wonder. Thanks so much for tuning into this explainer.